Okay, welcome everyone to this week's CDAC webinar. I hope everyone is doing well, having an enjoyable summer. Today it's my pleasure to introduce Janice Musfeldt from the University of Tennessee. Janice is a professor of condensed matter physics, experimental condensed matter physics, and physical and materials chemistry in both the chemistry and physics departments. Janice specializes in quantum materials and has worked on a variety of systems over the years using a range of techniques and probes, including high magnetic fields, synchrotron radiation, and other spectroscopies, as well as high pressure. In fact, Janice has been an active user of our CDAC and compressed-supported infrared facilities at Brookhaven over the years, and I hope she'll mention some of that work today. She's also trained a number of students who've gone on to the DOE national laboratories, including both Los Alamos and Brookhaven. I just learned that Janice is a native of Chicago. She has a bachelor's in chemical engineering from UIUC and a PhD in chemical physics from the University of Florida. She then was a postdoc at the University of Sherbrooke, and then an assistant and then associate professor at SUNY Binghamton before moving to the University of Tennessee in 2002, where she's risen through the ranks. So Janice, we're really delighted you're joining us and giving a talk today.
Okay, thanks so much for the introduction, Russ. Again, I'm Jan Musfeldt from the University of Tennessee, and today I'll be talking about quantum materials under external stimuli. And Russ asked that I begin this presentation with an overview of our spectroscopic program and explain how we got into high pressure work. And so what I thought I would do is discuss some of the advantages of combining pressure along with other external stimuli like high magnetic fields and so on, small sizes that we might be more familiar with. And I have several examples ready to go, depending on the time. And while I've been very lucky to have wonderful collaborators over the years, one of the constants that you'll see in all of this high pressure work is Zhenchen Liu. He's been a fabulous collaborator and friend for many years and was the one that really has enabled us to initiate and maintain a high pressure spectroscopy program. Okay, so as I said, Russ requested that I start at the beginning and really explain how we came to be involved in high pressure work. Well, and that story actually brings me back to graduate school. So it's a bit of a funny or sad story, depending on how you look at it. You know, I was basically a happy graduate student, you know, doing my science, doing my projects. Of course, we had to write an oral proposal about some idea that we had, and I had been reading some high pressure papers, and of course, I wrote my oral about some of that. But that wasn't the really challenging thing that happened. You know, there was this monster related to high pressure work in grad school that I'll tell you about in a minute. But mostly my career has been really smooth and with many exciting projects, science findings, and so on. So of course, everybody wants to know about the monster. So let's get that out of the way right away. The first project I did in graduate school was related to some of the organic molecular charge transfer salts, something like TTF, TCNQ that forms chains and it dimerizes or tetramerizes, and it undergoes these different phase transitions with what we would nowadays call charge ordering. And it turns out that if you have a look at the spectroscopy, what you see below the structural phase transition temperature is actually not only evidence of the structural transition, but of the charge ordering. You get this dimerization of the vibrational modes with all of these extra side peaks. And it turns out you can use their oscillator strength as an order parameter. Fine. Well, you know, I was always that kind of graduate student who had a plan to surprise my advisor. Okay. And so one day I borrowed a diamond anvil cell from my friend, and I had this plan that I would be able to take this organic charge transfer salt, apply pressure, and drive it into the metallic phase, and I would be able to quench this charge order and be able to see a druta come up. Okay, great idea, fine. The only problem is I didn't really know how to do high pressure work. And so a few things went wrong with the experiment. But let's just cut that part short and say that I broke the diamonds. Well, now here's a grad student with a problem, right? The diamonds weren't even ours. So I had to go to my boss and explain how I had this plan to make him very happy. But in fact, I broke the diamonds that didn't even belong to us instead. All right, well, I lived to tell the tale. All right. So years passed by. I did not do any high pressure work after that first experience. I said, okay, there's clearly a trick here that I don't know. And, I better go with something that has a little bit less risk. All right. So my team has been interested in multifunctional materials since that time. So for many years, we've been working on multiferroics. And these are materials that combine more than one of the primary ferroic order parameters. So these include ferroelectricity, ferroelasticity, ferromagnetism, and ferrotoroidicity. And very often these primary order parameters are extended to include other non-primary order parameters, such as ferrimagnetism and antiferromagnetism. In any case, the idea here is that we know that, for example, normally electric field works on polarization. Okay, but it turns out that in a multiferroic material, because of the cross coupling, you can also manipulate spin with electric field, and vice versa. You can apply magnetic field and manipulate polarization. So this branch of the triangle is a magnetoelectric branch, and that's where most of the research has occurred. It turns out that magnetoelectric multiferroics appear in many different forms. Of course, they appear in single phase form, like single crystals or thin films grown by epitaxy. You can make heterostructures, composites, nanoparticles, and so on. But one of the attractive things to us is that all this cross-coupling between the ferroelectricity, ferroelasticity, ferromagnetism, ferrotoroidicity gives rise to very rich phase diagrams. And I mean phase diagrams in pressure, temperature, magnetic field space, as well as size space, if you want to regard size as an axis. Okay, so magnetoelectric coupling, of course, involves breaking of spatial inversion symmetry, time reversal symmetry, and there are many different types of multiferroics as well. But for the purposes of this talk, it's probably just good to talk about a few commonalities and issues that we've been working on. So all of these couplings display hysteresis loops. So for example, there's the ferroelectric hysteresis loop, ferromagnetic ones, but then there are also the cross-coupled ones. There are domain walls in these materials as well. Ferroelectric walls, ferroelastic walls, and of course, magnetic walls. So there have been a number of challenges. One challenge that kind of goes across this field is how to raise the operating temperatures and increase the magnetoelectric coupling constant. A second challenge is to reveal the properties of domain walls. In other words, not just image them, but reveal their properties and then turn those domain walls into devices. So very quickly, I'll give you a couple of examples of what we've done in this area. Very recently, we've been attracted to a set of superlattice multiferroic films that are made of two different end members. There's the 124 version of lutetium ferrite, which is an anti-ferroelectric and charge ordered. It's very magnetic at 240 Kelvin. And the other end member is this 113 stoichiometry of lutetium iron oxide. And the idea is that by layering them in different patterns, you can create higher temperature multiferroics. Okay, so one of the things that we've been interested in is unraveling structure property relations in this family of materials, and then explaining the exact origin of this high temperature magnetic behavior. So it turns out that we studied three different lutetium ferrite superlattices. We studied the M=3 member, the M=7 member, and the M=9 member. And this one here has room temperature multiferricity. Okay, it turns out that as you increase the layering, the lutetium layer distortion becomes more and more rumpled. So we measured the magnetic circular dichroism spectrum of these superlattices. And by making constant energy cuts that correspond to different charge excitations, we can reveal microscopically what each of the different iron centers in this material is doing. So we can map out optical hysteresis loops, we can get coercive fields, remnant fields, and so on. Well, one of the things we did as part of this project was extract the interface response for the lutetium ferrite superlattices. And we did that for all three of these materials, the 3-1, 7-1, and 9-1 superlattices. And what that looks like is shown here. And this is maybe the most interesting aspect, is that we were able to reveal that while at low energy, oops, got the wrong thing, all of the superlattices behaved the same. At higher energy, where the iron 2+ to 3+ charge transfer in the spin up channel became important, that excitation became more and more important with these higher temperature superlattices. So in fact, you can see that here, and we're plotting in this last panel, we're plotting this remnant MCD spectrum as a function of the lutetium ferrite layers, and that's essentially as a function of lutetium distortion. And you can see that the only thing that changes there is the spin up channel charge transfer. The other thing we did with these materials was to unravel the charge ordering pattern. It turns out that theory can propose a lot of different charge orders for this type of material, especially in the 1-2-4 layer. But if you do the calculation, they're nearly isoenergetic. So what we decided to do was to use this formula and theoretically impose certain charge ordering patterns from a more extensive list. We chose some that were low energy, and then match them to the experimental magnetic circular dichroism. So we did that, and we could show that this non-polar charge order pattern is actually the winner. All right, so that's a project that worked out pretty well. And we had a lot of fun with it, but you know, this isn't something that was very amenable to pressure. Quickly, I wanted to give, so that work was done at the National High Magnetic Field Laboratory, and we do quite a bit of spectroscopy there. It's a user facility, and we've benefited from it quite a bit. We also work at Lawrence Berkeley National Lab. This is a photo that Mike Martin took, you know, when there were a lot of fires out there last summer. But what attracted us there was the near field setup that could actually do some spectroscopy. And as Russ mentioned in the introduction, my team really specializes in unusual types of spectroscopy of materials. So clearly we're interested in opportunities where we can use tip-based spectroscopies to get spatial resolution. And this particular case is really, it's quite remarkable. We have actually 20 by 20 nanometers squared spatial resolution, which is perfect for having a look at domain wells. So a lot of my research program deals with nanomaterials, and domain wells are a nano component in, of course, a larger functional material. So the platform that we chose for this work was calcium titanate, the 327 analog. It's an N=2 member of the Ruddleston copper family. And what makes it unique is that it's a hybrid improper ferroelectric, because there's this triclinic coupling mechanism with two different nonpolar structural distortions that add up to give you the ferroelectricity. They actually don't subtract completely. Okay, so here's an image of it, and very quickly, these same ideas apply at seem to have gotten stuck. The same ideas apply across a domain well. Okay, so you have these tilts and rotational order parameters. Fine. So calcium titanate actually has lots of different domain wells. There are ferroelastic ones that are actually straight here, like this. And there are ferroelectric ones that are meandering. And if you do a site substitution, you can increase the density of wells, but I'm going to talk about the parent compound. And of course, people have used all kinds of AFM-based techniques to image wells. But we're not just interested in imaging wells. We want to use spectroscopy as a diagnostic tool to reveal what the lattice is doing. Because if you want to make a device out of if you want to make a device out of some of these domain walls, like, oh boy, going crazy, like a racetrack memory, you need to care about how domain walls dissipate energy. So very quickly, again, this image, these contour plots are snapshots of distance versus frequency effects across several different domain walls in different crystals. And I'll just say that domain walls are like people. You know, everyone is different, but you can do constant frequency cuts and constant distance cuts to unravel some of their different properties. And what you can see is that these walls are all semiconducting. They're surprisingly wide. And in fact, you can map some of their properties back to predictions for order parameter behavior across the wall. And so we did that. I would say the agreement is, well, I guess it's okay. It's not terrible, but you can map the behavior of the tilt and also the rotation according and compare experiment with theory. And it's not too bad. All right, so fine. Again, we have a list of the usual suspects and a paper. We finally finished that paper. I'll add that Kevin here has been doing high pressure spectroscopy too, and he's going to graduate one of these days, and I hope somebody will hire him. All right, so years have passed, right? I have heard so many excellent presentations over the years. You know, Brian Maple and I hung out a bit in China, and I've always admired all of his high pressure and field work. I've listened to Bruce McComb's talks and also, of course, Dan Haskell's presentations. And, you know, I never gave up on the idea that I should try some high pressure work. So I don't know about you guys, but my mom read me way too many of these motivational books when I was a child. The little engine that could, and try something new. There's no limit to what you can do. Yeah, I hate that stuff, right? Um, but of course, then nothing can suppress this little light bulb idea I have that, I really ought to try high pressure spectroscopy. And it turned out that the ACS PRF program was offering small grants to people who had new directions to their research program in mind. And this is a little bit of a funny program because, the way I always like to describe it is that you have to propose an idea in an area where you know nothing. Well, clearly I knew nothing, because you can't propose an idea where you actually know something. That would be terrible. So I proposed that our team would learn how to do high pressure spectroscopy and combine it with our field work. And as part of this effort, we were really lucky to fall in with my friend Zhenchen Liu at the compressed beam line. And that was back at the NSLS-1. His specialty, of course, is Earth and planetary sciences, searching for metallic hydrogen and so on. And I've really spent many happy hours hearing about searches for metallic hydrogen. Anyway, about the same time, I had an excellent graduate student, Ken O'Neill, who's now at Los Alamos, who could be a guinea pig for some of this work. And we wanted to try high pressure, but without some of the complications that I was aware of in some of the systems, for example, that other people work on. So I was looking for a very easy problem, something that could be done at room temperature, something that would be, fun, something where I would not break diamonds, right? So I wanted to avoid, these unusual order parameter systems, for example, that Brian Maple studies. I didn't think that would be a good one to begin with. All right, so we launched our high pressure work, and that was back at the NSLS-1. And here on the lower left is a photo of the setup I used just a couple of weeks ago. And as you well know, of course, all you have to do is get light onto the sample through the diamond anvil cells, and away you go. And you can do any type of spectroscopy your heart desires. One of the things that I've really valued through the years is the high quality of theory collaborators that I have. And I found out that it's really very important to have good theory collaborations as you try to unravel high pressure effects in materials. So that includes lattice dynamics calculations, electronic structure theory, predictions for polarization, and so on. Okay, so let me tell you about one of our first projects. And, this is back in the days when chalcogenides, simple transition metal chalcogenides, were becoming popular again, maybe around 2013, 2014. There were reports of molybdenum disulfide incorporated into a transistor. My friend Yoshi Iwasa at Tokyo was showing superconductivity, in fact, ambipolar superconductivity in moly disulfide. And a friend of mine at the Weizmann Institute, Rashef Taneh, was making nanoscale transition metal chalcogenides, moly disulfide nanoparticles, tubes, and so on, and tungsten disulfide analogs. And just to enlarge what was on the prior page, his deal was not so much that you can study quantum confinement with these nanoscale analogs, but it turns out that he was interested in their remarkable engineering properties. So as you probably know, transition metal dichalcogenides are the world's best solid state lubricant. And it turns out that if you go to a nanoscale analog, such as these nanoparticles, it's 50, the solid state friction coefficient under high load is 50% better. So we've always been interested in the microscopic origin of engineering properties. And so I thought, okay, here's a great opportunity for some young student like Ken. Not only will we be super famous for sorting out some of this quantum confinement stuff and potentially high pressure metallization, but we're going to be rich as well because, of course, we're going to solve the problem of how these nanoscale chalcogenides lubricate so well. All right, so that alludes to another one of the reasons we were interested in this project. There were just reports coming out that the electronic properties of chalcogenides under compression were interesting, and that there could be gap closure that could be tested. And there was already evidence of metallization in moly disulfide, just due to collapsing this interlayer spacing. It turns out that the bulk tungsten disulfide was more stable though. And what we found is that when we tested the nanotubes, the electronic properties were different yet again. Okay, so here are some SEM and TM images of our multi-wall tungsten disulfide tubes. They're really very high quality. They're made at the Weizmann Institute in a fluidized bed reactor. And the idea is a very simple one, very chemical one, in a sense that pressure is going to act on the bond links and bond angles and change the phonon modes. And if we press enough, we'll be able to follow the degradation of the tubes and potentially the metallization of the material. So we weren't the first ones to try this work. It turns out that other guys had done some Raman work in the past under pressure. So what differentiates our work from that of the German team is that we measured both infrared absorption and Raman scattering under pressure. So as many of you know, it's the far infrared where the compressed beamline really shines, okay? And in fact, it's perfect for analyzing different kinds of chalcogenides. Okay, Raman scattering under pressure is much easier. And we also explored a larger temperature, a larger pressure range than the other team did, with the idea of getting a comprehensive view of the different types of lattice motions. The other thing that Ken did was that after he compressed material, released the diamond cell, he gathered the used material and we did a TM analysis on it. Okay, so here are the results. We have infrared as a function of pressure on the left-hand side, and then and Raman scattering as a function of pressure on the right. And okay, so like I said before, it's really this infrared that is the crown jewel of the compressed beamline. So there are some well-known vibrational modes here. There's this E1U, doubly degenerate interlayer mode, the A2U interlayer mode. And then Raman scattering also has a variety of features that harden with increasing pressure. Oops, well, that's not working out there. Harden with increasing pressure, and then when you release, it goes back. Okay, so we measured infrared and Raman up to 20 gigapascal. The mode displacement patterns of simple transition metal chalcogenides like 2H tungsten disulfide are well known. So we assume that the modes in the tubes are pretty similar in character. So we can track these results. And if you plot peak position as a function of pressure, what you get is shown here in the right-hand column. All right, we see that the doubly degenerate EU modes are almost bang on top of each other. They increase with a slope that's very characteristic of nearly all of these modes. The only one that's different is this AG, totally symmetric vibrational mode, that increases at a rate twice of the others. Okay, so looking more closely, we see systematic hardening of vibrational modes under pressure. Mode shifts are on the order of 1.2 wave numbers per gigapascal, very systematic. And we see that the only exception to that is this Raman active A1G vibration. It shifts at a rate about twice, a little more than twice that of the others. That's why it's in red here, okay? You see it's in red. We quantified these trends by calculating mode Gruneisen parameters. And so you can do that by extracting how the frequency shifts. Frequency shifts with, oh, darn it, shifts with pressure, and then multiplying that by the isothermal compressibility. In any case, you can extract volume and even directional Gruneisen parameters. And what they show is that the Raman active vibrational mode that has A1G symmetry is likely the driver of the tube breakdown. Okay, so tube breakdown method. So now we get into a little bit of theory and even some engineering. There have been first principles calculations done to provide insight into the lubrication and breakdown mechanism of simple transition metal chalcogenides in tubes. And the idea is that they predict that the innermost layer is most strongly affected. So as you compress, there's a crack that forms and it propagates from the inside out from what's called a pinching point in the innermost layer. And then this results in the formation of very thin two-dimensional sheets, okay? And remember, this is in the days when they didn't know much about few layer systems and monolayers and sheets. Okay, so there are also shockwave experiments that predict a similar mechanism, except the fracture in that case originates in the outermost layer, not the innermost layer. And I could play this simulation one more time if you wanted to have a look at it. Let's see if I can get it. There we go. Hey, come on. Come on. There we go. Yeah, so it tends to break like right in here, okay? You can watch for it. Oh, I'm sorry. Really? Oh. Fabulous. Are you guys still there?
Yeah, we're here.
Okay.
Press on.
Sorry about that.
No problem.
So much for clever simulation, right? Okay, so all right, so what I wanted to say is that we can compare our findings, our infrared and Raman under pressure with theory, with simulation, with shockwave experiments. But the other thing we did is compare with direct TEM images. So we took the material from inside the diamond anvil cell and had a look at it. And in fact, you really can see that it's fracturing from the outside in. And you can even start to find different well, I guess, evidence of sheet formation. Okay, right here. You can see a few layers forming. And right here, you can see breakage from the outside in. Okay, so what about electronic properties under pressure? It turns out that these experiments really provided very unexpected insight into the electronic properties. The far infrared reveals a very broad and rising electronic background under pressure. So in fact, what I showed you before of, just the phonons here like this was a little bit of a cheat, right? I changed the frequency axis so that you could see only a close-up view of the phonons. But if I show you this view from low frequency up to much higher frequency, what you see very clearly is this very broad, localized absorption. Okay, so if we calculate a different spectrum, say absorption under pressure, minus that at zero pressure, what we subtract then is this gradually rising background, and we get this kind of thing shown here. Okay, so this is really just an absorption difference, emphasizing the growth of this localized absorption in the far infrared under pressure. And so, in fact, we could model this effect by percolation dynamics. So what we think is happening is that we can go from relatively isolated tubes at low pressure where there's hopping to touching tubes at elevated pressure where, in fact, the tubes where there can be some conduction. But while the individual tubes may be relatively conducting, the ensemble properties are dominated by hopping from tube to tube. And that's the origin of this far infrared excitation. Okay, so eventually we wrote that up and the project ended well. Here's a photo of Ken again. I should add that Ken is now looking for a permanent job, so he's terrific if somebody wants to snap him up. Everybody knows Zenshan, and these are my collaborators from Israel, Ala and Russia. Okay, so I want to stick with chalcogenides for a minute, maybe a couple of minutes, and tell you a little bit more about our work on high pressure properties of these materials. And I want to talk about some complex chalcogenides now, not just simple transition metal chalcogenides like moly disulfide or tungsten disulfide, but I want to go to something more complicated like manganese PS3 and others of that ilk. So as you probably know, people are realizing that just like oxides, these van der Waals materials are exceptionally responsive to external stimuli, and that tuning parameters like pressure or strain can alter the balance of energy scales and drive materials into new areas of phase space where you can get exotic properties. So this is, of course, our strategy with high field experiments too. And certain things have already been reported, such as pressure-induced layer sliding, metallicity, and even superconductivity in these complex chalcogenides like manganese PS3, iron PS3, or chromium silicon tellurium 3. But guess what? There's more. And one of the things that we found early on when we went back to the light source after the dark period is that we discovered piezochromism in manganese PS3. So this is a very attractive thing. The idea is you take this kind of greenish colored crystal, you apply pressure, and you can get it to go from yellow to red to black. Okay, so not even transmitting light at all, black. And then when you release pressure, back to yellow again. So that was pretty exciting. And all of these pictures were taken with, I think, Nathan's or Ken's cell phone. Okay, and at the same time that we decided to explore the piezochromism in manganese PS3, we were also having a look at sheet effects. So the idea that we could thin these complex chalcogenides down to the atomically thin single layer limit and use near field techniques to study them. So we were doing pressure and near field at the same time and hoping that they would be complementary. All right, so very quickly, here's what we found. The optical properties of manganese PS3 are pretty straightforward. This is absorption versus energy. And what you can see right here is the charge gap, okay? So it's basically a charge transfer. And what happens under pressure is it just moves to lower and lower energy. You can do a direct gap analysis by plotting alpha E squared as a function of energy to extract the exact value of the gap. So here at ambient conditions, it's something like 2.6 or 2.7 electron volts, and at something like 11 or 12 GPa, it's down here to 2.1, I guess, or 2.15. All right. We can plot the trend in the direct gap on a gap versus pressure plot. And the data I just showed you gives you this trend right here. So what's really neat is that we have deterministic control over the position of the gap. It's linear in the visible range. And in a sense, that's very much what we could see from these photographs, right? Oh, we didn't know the gap was linear. Okay, we also know that at about 20 gigapascal, the band gap moves out of the visible range. Okay, so what seems to be happening here is around 10 gigapascal. There's the sliding transition. What happened here? Well, there's a sliding transition. The system turns black at about 20 gigapascal as gap moves out of the visible range. And then eventually there's a metal insulator transition up here at about 28 GPa. All right. Uh-oh, no. You know, all of this technology is not always what you wish for, right? Oh, here we go. Okay. So let me just clear this off for a second. Oh, it's still there. So I want to explain also where we can get these points here, right? So as soon as we can detect metallicity, we know that the band gap is closed. And so we went to the middle infrared to observe the formation of the druta. And we can also see whether the band gap is coming into the middle infrared. All right. So what you see then is if you look at the far and middle infrared, you can see metallicity develop above 28 Tesla. Here's the druta. And a close-up view shows a phonon, strong phonon, that's a PS stretch at ambient conditions. And then there's the druta that appears at 28 gigapascal. So the gap is closed. But there are also very weak structural transitions at each of these sliding and metallicity crossovers. But they're really characterized just by small changes in slope of the frequency. They're very, very subtle. Okay, so the neat thing here, deterministic control of the band gap across the visible range at room temperature. All right, so this ought to be useful for something. Well, what does theory say? Well, theory worked out how the band gap closes as well. Starting with the C2 upon M structure, that's a staggered phosphorus dimer. They show that at 10 gigapascal, which is where we have sliding and a very subtle rearrangement of layers, we end up into this aligned phosphorus dimer phase. And then at a higher pressure where the system goes metallic, we end up with aligned phosphorus chains. And there you can see that the gap closes. I've just enlarged this a little bit so you can see that there's a finite density of states at the Fermi level there. Okay. Good. Bright. Not good. Okay, so this work was led by Nathan, and he's going to come onto the job market pretty soon. I hope somebody will hire him. And again, here's Zhen Chen and all of the usual theory and crystal growing suspects. All right, so years have passed by, and one of the things I was always waiting for was the development of some molecule-based multiferroic materials, because you know that molecule-based compounds are highly tunable on account of their low energy scales, their very flexible architecture, the fact that you can do chemical substitution, and also they're well known to have experimentally accessible magnetic fields. And one of the systems that attracted our attention was this metal organic framework system. So there's an ammonium, this is essentially an ABX3 compound, just like a perovskite, except that we have an amine that is an amine in the chemical formula up here, manganese, and then it's connected by formate linkers. One of the attractive things with molecule-based multiferroics is that you can go searching for different kinds of quantum phase transitions, particularly magnetic quantum phase transitions along the lines that Sergei Budko was talking about a couple of weeks ago. Really. So there are a lot of field-induced transitions to explore, particularly to the fully polarized state. But one of the most attractive things about molecule-based materials is they're soft and flexible and squishy. And so immediately that gets me thinking about what we can do with pressure. So with pressure, we can also develop phase diagrams, reveal properties, and so on. So we already knew quite a lot about the high magnetic field properties. We developed the magnetic field temperature phase diagram of manganese MOF by measuring magnetization in pulsed fields, and Mike Wangbo did some spin density calculations, and we could map out the magnetic field temperature phase properties and to show which phases are in competition with each other. And we also did magnetoinfrared to show how a single phonon mode, in particular, the formate bending mode, links the ferroicities with temperature, as shown here as an order parameter, and in magnetic field, as shown here, and it behaves as an order parameter in both cases. So fine. So this manganese MOF is really quite interesting under external stimuli. At high temperature, so the manganese centers form a square. They're connected with these formate linkers, and essentially the manganese is in an octahedron. The amine sits in the anion pocket here, and it's above the order disorder transition. At 185 Kelvin, it's disordered, and then it orders and engages in long-range hydrogen bonding at low temperature. So the superexchange pathway is really simple. It just goes from manganese through the formate ligand to the other manganese. And we already know a lot about what happens in magnetic field. There is a spin flap transition, and then at 15 Tesla, a transition to the fully polarized state. So with temperature, though, the high temperature phases, R3 bar C, go through the ordering transition. System goes to a CC, symmetry phase. There has been another group that had a look at pressure effects at room temperature, and they proposed that the system would go through a transition to CC under pressure as well. But in our hands, that's not what happened. It actually went to a completely different and unexpected phase. So that's what I want to show you. So we took a look at what happened to the manganese muff, multiferroic, under compression. We always do a full room temperature survey first. This plot summarizes Raman scattering as a function of pressure, and it highlights the behavior of some low frequency modes, the formate bending mode here in the middle, okay, and also the CNC stretching mode at higher frequency. The key, though, is that at room temperature, we start with this R3 bar C phase, and then we go through this wide mixing range shown here in purple. So it's essentially a mixed phase region of R3 bar C plus some unknown phase, which kind of later I hope to convince you it's P1, and then into the P1 phase, and finally into an amorphous phase. Okay, since the behavior of the formate band is such a great indicator of the transition, we're going to go with it. And like I said, it's a great indicator of the transition in magnetic field too. Okay, so what's going on with the symmetry? We know that temperature drives the system to lower symmetry. Okay, we can see that the system goes from R3 bar C to CC across the order-disorder transition at 185 Kelvin. And the vibrational properties do not change at the magnetic ordering temperature at 8 Kelvin, at 8 K. Okay, so we carried out high pressure experiments above and below the ordering transition. And what we see is pretty interesting. I'll just have you focus on this formate bending mode right here. Okay. At high temperature, it's a doublet, okay? And it eventually gets this triplet-like structure, and then finally, this additional feature right here. Below the order-disorder transition, it starts as a triplet, okay? And it continues as a triplet, and eventually it goes into the higher pressure phase, and you can see the development of this low frequency shoulder as well before it goes into an amorphous phase. Okay, but the neat thing is that that's totally different than what happens with pressure. So if you examine what happens just at ambient conditions under temperature, you see you start at 4.2 Kelvin with 3 features. Okay, and you can go to higher and higher temperature. This is the R3 bar C. Here is CC, but the CC phase does not have this extra feature here that I pointed out to you here and here in the pressure effects. So we can conclude then that it has to be a lower symmetry phase. So if we have a look at the symmetry subgroup of R3 bar C, now here are our starting positions. We know this is a room temperature starting phase. This is our low temperature starting phase. The low temperature phase has only one subgroup. So if you're going to a lower symmetry phase, it has to be P1 bar, and same deal at room temperature. Okay, so we can bring all of this together in a pressure temperature magnetic field phase diagram. Okay, and you know what I've really talked about here is this, pressure temperature axis, but I've added on our magnetic field data just so that you could see how it all goes together. So if you sweep pressure above the order-disorder transition, what you see is you go from R3 bar C through a mixed phase into P1, and then eventually to an amorphous phase. If you sweep pressure below the order-disorder transition, You also go from a CC phase into a mixed phase, and then into the P1 phase and amorphous phase. Great. So we can, what I want to point out next is, of course, P1 is a polar space group. So immediately we see that there's the possibility of getting a ferroelectric response, potentially at room temperature under pressure or strain in this organic molecular multiferroic. Now, we don't know whether manganese MOF is ferroelectric or pyroelectric. In other words, whether it's switchable or not switchable, but we do know that P1 is a polar phase. All right, continuing with the development of the phase diagram, we got a friend of ours to have a look at how the Néel temperature evolves under pressure. And we added that to the phase diagram right here. Okay, so what we see is that bringing together a variety of spectroscopic techniques, we can develop the pressure, temperature, magnetic field phase diagram for manganese MOF, an organic molecular multiferroic. So not only does it have a room temperature polar phase, it has a unique mixing phase, it has a magnetic quantum phase transition, and so on. And the distortions of the formate ligand are crucial for driving all of these phase transitions. And of course, this new polar phase at room temperature is really interesting. I just want to point out the similarity with an AbO3 oxide multiferroic. This is terbium manganese oxide, and it's work by Chiyoshi Kimura's group. And what they found is that under pressure, above about 5 gigapascal, they could drive their system into a polar phase with a much larger polarization. So that's the hope, obviously, in this case. It's something that is for the future. Okay, so that work was by Amanda. She just finished up in my group, and the paper came out quite recently. So have a look at it if you want to know more. So I'm very sure my time is up. I'll just conclude by saying that combining pressure with magnetic field, temperature effects, and small size effects is the best thing I've ever done. It really opens the door to an entirely new set of opportunities. I've had a lot of fun at the compressed beamline. It's a wonderful facility led by one of the best spectroscopists in the world. And if you haven't been there to try it out, I would urge you to do that. Okay, so this is a recent picture of my research team from May. Amanda, who did the work I just showed you on multiferroic manganese MOF, is headed to Miami University of Ohio, I guess next week. Sabina got a job at the Brookhaven National Lab Nanoscience Center, and Shiyu just started a job at the National Synchrotron Light Source doing RIGs. All right, and I'll thank NSF and DOE for support of this work and take your questions.
Thank you very much, Janice, for a delightful talk. Beautiful work. The floor is now open for comments, questions. Just unmute yourself or put your question or comment in the chat, or raise your hand. It's great to see these combined pressure, temperature, magnetic field phase diagrams.
Yes, they're really rare, aren't they?
Yeah, and
yeah,
maybe I'll ask the same question I asked Brian last week about sort of combined pressure and magnetic field measurements. Do you have any plans to do that, for example, at the Mag Lab?
Yeah, I think that would be extremely interesting, and I would definitely like to do it. On the other hand, I think there's a lot of room for simply extending, for example, this phase boundary here a little further to see whether any crossover is triggered by any of these phase boundaries. And you can also imagine that there are some different arcs connecting, for example, a field axis with a pressure axis. So I would expect there to be some kind of pressure-driven field transition. Yes, I think we should explore using multiple parameters and multiple tuning parameters at the same time. It, of course, makes it harder to get things done in 1 week of beam time or magnet time, but that's the price we pay, right? This particular phase diagram is the result of, many years of work. And there are still regions where, we don't know much, right? But it just gives a wonderful view of how the different phases compete, and also how they support each other.
Right.
In this type of material.
Jen, here's Dmitry from Magnet Lab.
Hey.
Thank you very much for a wonderful talk, and this is a very inspiring phase diagram. It was inspiring me for quite some time to try to combine high pressure and high magnetic fields.
Yes.
So a few words about latest development. I think we are very close to be able to run high field measurements with pressure up to at least 10 GPa for visible spectroscopy like Raman or KL.
Yeah.
I'm not sure about infrared. We don't have bright source, just usual things. But for visible optics.
Yeah, but look, you have to start somewhere, and doing the Raman scattering under pressure or photoluminescence is a perfectly reasonable way to start. And so yes, obviously, Dmitry, I knew about this effort. I've written many letters on your behalf, as you know. I just didn't feel like it was my place to talk about it, so I'm glad you did. But yeah, I don't think that every technique has to have it available, but some number of techniques should. And it's really important to get beyond, just some of the simplest things of, to get site-specific, microscopic, local probes. That's the kind of thing that Raman or photoluminescence or infrared can provide.
And I have a couple of questions. One, so of course, in all these studies, IR or Raman, polarization information could be very important. Yes. Did you perform any polarization analysis? Did you see any changes of polarization?
Yes. All right. Yes. Okay, so that is ongoing, and of course we ask those theorists, right?
Okay.
But they have their own timetable that they live on, and they'll let us know when they're good and ready. But it really is quite interesting that terbium manganese oxide hosts a very similar sort of thing. But this result, you'll notice, is at 20 Kelvin. Ours is at room temperature. Right?
Yeah, and another question. So among these materials, what do you think about uniaxial pressure or strain?
Yeah, sure. So if I was going to make a device out of this one, honestly, I'd slap a couple of strain gauges on it and see if I can get it to dry, see if I can drive the transition with strain. And if I could, do that at room temperature, that would make it super easy to actually measure the polarization, right?
Yep.
Yes. So to me, that would be the way toward a device.
I see. Okay, thank you.
One of my students who's listening could go and do that if you have no time tonight.
Okay, thanks very much. More questions or comments?
I have a quick question. Hi, John. This is Daniel Haskell.
Oh, hey.
How are you?
Yes, fine.
On one of your
Thanks for
first
coming.
examples, I think you showed data on a multiferroic and showed MCD data for
Yes.
0 Tesla and 25 Tesla. And the 0 Tesla data, is it magnetic resonance or is it some chiral non-magnetic circular dichroism?
You are very observant as usual. You always ask my best questions. Let's see. It's this. Okay. So one of the things we always do when measuring a multiferroic is that we do a training loop because there might be some hysteresis in the material. Okay. And you'll notice that what we have here is that we have a 0 plus and a 0 minus.
Okay.
And that just means we're sweeping up or sweeping down. So in other words, the zeros aren't the same. And you can see that right over here, right? That if you're sweeping, say, up in the blue curve, the 0 is here, whereas if you're sweeping down, it's here.
I see.
Okay, and
I see.
the point is that these different optical hysteresis loops are taken at different energy cuts. So one of them is probing the spin up channel charge transfer, and the other one is, and you see how it's flipped, is probing the spin up and spin down channel excitations.
Yeah, no,
So
that makes
kind of
sense.
cute. So yeah,
that
but
is
there
cute.
is a loop, absolutely, and you have to take the loop, in other words, run the field across the loop without taking data for an hour. It's really dull before you can take data.
No, thank you. I see there is field dependence, so it's
Yeah.
certainly magnetic. Thank you.
Yeah.
Thank you. Animal from UIC has a question.
Hi, thank you very much it was really great talk with cool graphics.
Oh, thank you. Yeah.
And I really appreciated your stories. It was really fun and exciting to know about your
So are
journey.
you in Russ's group?
Yeah.
Oh, so you're going to have stories of your own.
Right.
So you appreciated, let's see, you
Yep,
appreciated this.
Yes.
Okay, like out, get out now. Okay, what's your question?
Right. So you showed so like in a simulation, percolation simulation,
Yeah.
and prove that basically showed the rising electronic background under
Yeah.
pressure. I was wondering how how you concluded that based on the simulation, or how the simulation was.
Yeah. I probably went too fast. Okay, so I know that I did explain that I was showing you close-up views of the phonons before, right? But if you look at this full far infrared range, which is of course what the compressed line is the best at. This is really built for one purpose and one purpose only, and it's far infrared and pressure. Okay, and so this is absorption as a function of frequency in the far infrared. And you can see that there is this rising slope, right? So at ambient conditions, probably this thing is peaking way out here, right? In the middle infrared. Okay, but when you apply pressure, it's clearly moving into our frequency window. And this hump grows and grows and grows, and eventually at 20 gigapascals, it's quite prominent. So we wanted to be able to analyze it. And so we calculated an absorption difference, because sometimes absorption differences allow you to focus on particular changes. So that's what's shown in the next plot. And of course, this difference shows changes in phonons, but we're ignoring that and simply looking at this big hump, right? And then we did a very simplistic thing. okay, we took the intensity of this hump at some position, say here, right? And plotted it as a function of pressure. If you do that, you get these blue points here. And if you fit with this percolation model, what the intensity should look like, wow, it's pretty bang on. So what it shows then is that you go from a case where, so you always have an ensemble of tubes. This is not a single tube measurement. We could, in principle, do that with near field infrared spectroscopy. But for an ensemble measurement of isolated tubes, you still have this charge transfer or hopping between nano objects. And that hopping is pretty clearly moving into the far infrared. So I suppose if you were to press and maybe get up to 100 GPa, you could drive this to 0 and get a Druda. Okay, but in this pressure range, there's no metallization, unlike a lot of the very traditional chalcogenates that are layered. Remember, these are tubes. Okay, so it kind of makes sense that eventually you're going to have charge hopping from tube to tube, and that's percolative. Okay, yeah.
Awesome. Thank you very much.
Sure.
More questions or comments?
Hi, Jen. Great talk.
Hey, thanks.
Yeah, I just want to make a comment. So basically, you covered pretty well about our facility, but we also can do like in situ high pressure and high temperature.
Oh, yes, that. Yes.
And also we have a neighbor IR beamline, which they are already developing the near field capabilities. And also
right.
we have like a magnetic
That's
magnet.
right.
So eventually there will be a potential to have the near field and high pressure, high magnetic field together at SLS2.
When that happens, I'll eat my hat. That's going to be really hard, but okay, I'm ready.
And basically all within the same hutch. So
Yes, all at the same time. That's what I mean. It's just that, well, it's going to be tricky to, it's already Hero's work to do near field spectroscopy at low temperature. Putting it in magnetic field is even harder. Putting it in some kind of pressure chamber, harder still. And yeah, bringing it all together, that would be great.
okay, thanks very much. On that point, I wanted to mention that, as you know, the beamline is supported by NNSA through CDAC, as well as through our compressed grant. So it's jointly funded by NSF and NNSA.
Okay, so we should call it the CDAC compressed beamline?
Right.
Okay.
NNSA, right.
Will do.
Okay, there are no more questions? Let's thank Jess for a delightful talk. It was a lot of fun, beautiful
Thank you,
measurements.
Yeah.
And we'll see you next week.
Good. Bye.
Goodbye.